Welcome back to this video on S2. Today we're looking at using the Poisson distribution to approximate the binomial distribution. And over the next few videos we will be looking at other approximations. Now if I've got a binomial distribution like so, and if it meets certain requirements, and these are quite simply if n is large and p is small. If I meet those requirements, then I can use a Poisson distribution to approximate it. Now, if you think about the Poisson distribution, that is going to be, y is with Poisson and it's going to be lambda, and lambda is going to be n multiplied by p. And a good little kind of hint here, now this is the first approximation we're doing, but we will be looking at some more as we go through the next few videos. So a good hint as we go forward is that if that np is less than or equal to 10, then usually this Poisson distribution is a good one to use for the approximation. So I'll pop that down here. So you're really looking at this. It gives you an idea. It's not perfect, but it gives you an idea that you can use the Poisson distribution as approximation for the binomial distribution. Now let's just talk about why this works. Well, it's quite simple really. If you think that e of x is np, isn't it, for a binomial, and the variance of x is np 1 minus p, isn't it? So what we get is that if p is very small, then 1 minus p will tend towards 1, won't it? Which will mean the variance will be np and the mean will be np. And if we think about Poisson, the mean and the variance are the same thing, aren't they? So, this is binomial here, and when I think about Poisson, its mean and its variance are the same size. So if we've got p being very small, this is going to be close to 1, which means that this is going to stay close to np. And that larger the value of n is, the better this approximation would be, because it would mean that these two would be much, much closer. So hopefully that makes sense. Let's have a look at the first example. So first we're going to use the binomial formulas, etc., to work this out. So if I look at a part 1, we're looking at the probability when x equals 4. So for this, I want to use my formula. And n is 150, isn't it? And we're looking at the value of 4. Then we've got 0.04 to that power 4 multiplied by 1 minus 0.04 to the power 146. And then I just need to go to my calculator. And as usual, I'm going to put this to 3 significant figures, so 1, 3, 4 there. Now, part 2, we can see here we've got a less than or equal to, but we're not going to be able to use our tables for this, so I'm just going to go ahead and put this straight into my calculator. So first we want to go into menu, then we want number 7, and scroll to it or just click the number 7. Now for A part 1 we could have used this binomial PD. Obviously we've already done that, it's just as quick to use the formula. So let's look at part 2. So for this we need binomial CD, cumulative. So that's number 1. Now I only want to do one of these, so just variable is fine. X is equal to 3 because it's less than or equal to 3. n is 150 and p is 0.04. Pearson equals gives me 0.1458 to 4 decimal places, which we do often have on here, or 3 significant figures, 146. So just writing that down properly, we've got x less than or equal to 3, and this is 0.1458 or 0.146, and that is obviously to 4 decimal places or 3 significant figures respectively there. Now for part B, I'm going to do this in a nice purple colour. Part B, we're going to use the Poisson approximation. It does tell us in the question, but obviously in the exam that's going to be quite rare. And the first thing I want to do is find out my value of lambda. And lambda is NP. So here we've got 150 multiplied by 0.04. And that gives me 6. So I'm going to call this y now, as we're looking at an approximation. And my value of lambda is 6. It's worth noting that I would say like 99% of the time, if you get asked one of these questions in the exam, this value of lambda should really be a value that's in your tables. I have seen the odd question, I think, in the past. I'm trying to think back now. But it's really hard to even think about it. You know, pretty much every question I've seen always has this value of lambda as a value that's in your tables, so that doing the approximation actually would save you time. Because if you think about it, if I wasn't able to look up values within my tables, then doing a Poisson approximation might take the same amount of time as doing just an accurate binomial, at which point you've got to ask yourself, why even bother doing the approximation? So for that kind of reason, I would say that this should in general be a value within your tables. So let's look at part 1 first of all. So here we're looking at where the probability of x equals 4, which I have changed to y. I could have actually left it as x, I suppose, in this case. And what I'm going to do is I'm going to use the formula for Poisson. So just thinking back now, that should be e to the minus lambda, so e to the minus 6 times 6 to the power 4 over 4 factorial. And we get 0.1338, 526, and so on. You can see this is very, very close. You know, 1338 is here. That's a 0 after it, that is a 5 after it, which would make it slightly different if you were rounded to 4, but we're going to round to 3 significant figures. So 0.134 to 3 significant figures there. So you can see that is the same as my first value. Now, part 2, we're looking at x being less than or equal to 3, or y being less than or equal to 3 in this particular case. And again, now I could use the calculator, but I'm going to obviously use the tables. And then looking up 3 in my tables, I get 0.1512, which actually is a little bit off from my first answer. You can see it's actually corrected 2 significant figures rather than 3 in this case. This is still perfectly valid as n is large and p is small. Okay, so it is always going to be slightly different with the more values that you're kind of taking in within this approximation. So for part A, and this is kind of based on an exam question, We want to suggest a suitable model. It's obviously going to be binomial here with our N and our P. Kind of obvious for, statistics too, as we don't have a lot of choice. So what we're going to do is let X be the number of damaged cells not always the fastest writer there. So it's just looking at what is in this question. Each cell, certain insect contains this many genes. It's known that each gene has a probability of being damaged. So we've got a suggested model for the distribution of the number of damaged cells in the cell. So damaged genes in the cell. So you can see I've already made a really silly mistake there. So let X be the number of damaged genes in the cell. Okay, and we're looking at, as I said, binomial. So X is distributed, binomial distribution, N is 1200 and P is 0.005. So it's just a matter of kind of taking this from the question and then writing down your distribution. Now part B is all about the mean and variance, and the mean of a binomial is N times P, so it's 1200 times 0.005. So just go to my calculator, 1200 times 0.005, and that actually gives me a mean of 6. And the variance we'd expect to be very close to this as well, wouldn't we? So if you remember, variance is NP, which is going to be the 6 multiplied by 1 minus P. So we're multiplying the 6 by 1 minus 0.005. And that gives me 5.97. So you can see here our mean and variance are incredibly close to each other. So it does mean it's going to be a Poisson distribution. And of course we could have got that from the beginning. NP, N is large, P is very small. And then finally in part C, using a suitable approximation, this is going to be Poisson, isn't it? Find the probability that there are at most 4 damaged genes in the cell. So I think I'm just going to keep it with X in this one. Let's call it Poisson. Lambda is going to be 6. At most 4 damaged. So that means we're looking at less than or equal to 4. And then of course it's just a matter of looking up in my tables. And luckily we've already used lambda equals 6. That makes this so much easier. So there we have it, 0.2851 to the 4 decimal places from my tables. And there we have it, 2 examples, hopefully not too difficult. And as always, a few questions for you to try and the answers at the end. Before you do jump to the questions though, just trying out a new microphone sound setup. Let me know what you think of the quality. Is this any better than the previous videos? Shall I go back to them in terms of how I was recording with sound? Is it loud enough? Just trying to get a better quality of sound, because that's probably one of the most important things in these videos. So just pause a second, let me know in the comments down below. Much appreciated. Now for part B, part A was straightforward, but for part B we do have a few issues. So what we want to do is we want to let our new distribution we're going to call y, and that's going to be 200 minus our x. So what that means is that my y is going to still be 200, but the probability is going to be 0.05, which gives me my nice small value, okay, which is going to be important over here. Now, looking at this one then, probability when x is greater than or equal to 196, well, turning that into y, we can quite clearly see that y is therefore going to be a less than or equal to 4, because all we're doing is substituting this 196 into here. And then from my calculator I get 0.02644 and so on, which is 0.0264 to 3 significant figures. Now with part B we do need to use this distribution, isn't it? Because it needs to have n large and p small. So we must be using this one. Sorry, that should be binomial. Pop that b in. So 200, 0.05. So when we look at our approximation now, we need to do 200 times 0.05, and that is going to give me that lambda is 10. Should be straightforward from here. So we are looking at now, instead of 194, remember I'm just using this, so substitute the 194 into here. 200 minus 194 is 6. So I can say that the probability when x equals 194 is the same as the probability when y equals 6. So that is e to the power 10, sorry, minus 10, isn't it, times 10 to the power 6 over 6 factorial. And that gives me 0.06355 and so on, which is 0.0631 there to 3 significant figures. So pretty close to our first answer. And then when I look at part 2, so this we're looking at obviously when x is greater than or equal to 196. So we are looking at this being the same as when y is less than or equal to 4, as we're going obviously in the opposite direction. And again, in this one, it's just a matter of going to my tables. And here we have the 4, so that's 0.0293, which again you can see is not too far off of 0.0264. So that is the approximations and the actual ones. So here we can see it's a binomial distribution, and what we've got to use is a suitable approximation. So you can see we've got a percentage of just 2% probability here, and 180 for a value of n. So large N, small p means that this should be a Poisson distribution as the approximation. I know that's kind of obvious, as that is what this video is all about. But obviously as you go further forward, these are the kind of questions you need to ask yourself, as you'll have more than one option. So my NP, which is my lambda, is going to be 180 times 0.02, which is 3.6. So in terms of my distribution, we are now looking at Poisson 3.6. That is obviously for the approximation. Now, one patient, so probability when x equals 1, and then using the formula, we've got e to the minus lambda times lambda to the power 1 over 1 factorial. And that gives me 0.09836 and so on, or 0.984 to 3 significant figures there. Looking at part B, at least 2 patients with the condition. So probability of greater than or equal to 2. So this is going to be 1 minus the probability that x is less than or equal to 1. Now 3.6 isn't in the tables, but less than or equal to 1 is just quite simply means we're taking away equals 0 and we're taking away when x equals 1. Now x equals 1 we've obviously already found, and when x equals 0, that's a nice one, isn't it? Because we get e to the minus 3.6 lambda, and then we have 3.6 to the power 0, which is 1. 0 factorial is also 1. So here I've got e to the minus 3.6 minus my 0.984. Oh, sorry. I almost... Actually, I kind of have messed that up, haven't I? Missed out the 0 earlier. So 3 significant figures, it's 098, isn't it? As the next number was 3. So that's what we're looking at. Obviously, I'm going to use the full value of this in. So I'm just going to take this full value as it's already in my calculator. I'm going to add to it e to the minus 3.6. And that will give me 0.12568 and so on. 1 minus that, and I get 0.8743 or 0.874 to 3 significant figures there. Now, this one we can see again, it is binomial. You know, we've got our probability of growing over 2 meters and we've got a random sample of 50 tomato plants. Now, find using a Poisson approximation. So this is obviously not really an exam question, as it often will, it's very rare for it to tell you to use a Poisson. But yeah, so we know we've got Poisson, and we know that anyway because that's what this video is about. And what we need to do is then find it between 5 and 8, including them. So let's first write down our distribution. So we got lambda is NP, which is 50 times 0.08. So 50 times 0.08, and that gives me lambda is 4. Remember, you want this value to be less than or equal to 10. Now we've got that, we can find our probability. So it's between 5 and 8 inclusive, so includes 5 and 8. So this is going to be the probability where x is less than or equal to 8 minus the probability when x is less than or equal to 4. Because obviously we want to get rid of 4 and below, and that will leave me everything between 8 and 5, including those values. Now, we've got lambda equals 4, so we can actually just go to the tables on this one. So 8 is here, 0.9786 minus, and then looking at 4, we've got 0.6288. And all I need to do, as always, is just pop this in my calculator, which I'm just doing now. And that gives me 0.3498, or again 0.350 to 3 significant figures. I would say that often we will leave things in 4 decimal places when it does come from tables and things. But as I've said, you know, in previous videos, the front of the test front of your actual exam paper, it says 3 significant figures. So, sticking to that will mean that, you shouldn't have any issues. I always like to put the values down first and then round though. Okay, just to be concrete, clear to the examiner. Final question. We can see we've got percentage or probability here 2.5% and n is 200. It's clearly a binomial distribution. We are, we're finding Poisson. Nice and easy here, already told us. So before we go ahead, let's work out the Poisson distribution. So we want to find lambda. Lambda is n times p. So it's 200 times 0.025. And that should give me 5. I just double check in my calculator. Yep, just double check in my mental maths there. So we got lambda is 5. Now we want the probability when x is more than 6. So that's greater than 6. So that means we're looking at the probability where x is greater than or equal to 7, which is 1 minus the probability of x being less than or equal to 6. Remember, always change to where you've got your inequalities with an equal. Doing that consistently is where you avoid silly errors or careless mistakes. Now, 5 for lambda is going to be in our tables, so I'll just pop our tables up now. So 6 within my tables is 0.7622. And 1 minus that, so we got 1 minus 0.7622, and that is 0.2378. So that's the 4 decimal places. I will often leave it as 4 decimal places when I be dealing with the tables, but obviously 3 significant figures, as you've heard me bang on about, that's what it says in the front of the exam. That's always the safest kind of option to leave your answers when it doesn't give you any other indication in the question. But I will always write my answers to more than that decimal places on the kind of line before. Now, part B, we've got a carpenter buying 6 packs of nails. Estimate the probability that half of these contain more than 6 faulty nails. So you'll notice the more than 6 faulty nails is what we did on part A. And the fact that now we're bringing in another number of these items is going to be a binomial. So you've actually gone binomial to Poisson and back to binomial. So let's write down our distribution. It's binomial. N is going to be 6 in this case, and our probability is going to be 0.2378, as it's the probability from before. And I would use that kind of larger value. If it was even larger, if it wasn't from the tables, I would have stored that in my calculator and used the full value in the question. Now we want the probability of more than half. So this is when y is greater than 3, more than half. So this is y is greater than or equal to 4, or 1 minus the probability when y is less than or equal to 3. Now this is the type of question where that probability is not in my tables, and because it's less than or equal to 3, that means if I worked it out individually, it would be equals 0, equals 1, equals 2, equals 3. So it's quite a bit of working out. So it's when I probably get to a question like this is where I would be using my calculator. And pretty much solely using it, not writing down anything else other than what I've already written down here. But I would, as you can see here, I will write down some of these values. So it's 968,475 and so on. And then I need to do 1 minus that. Always easier to store it in your calculator first. and that should give me 0.0315. Obviously it carries on, but I'm going to go straight in with 3 significant figures there. And that is all there is to it. So this end bit here is just straight from calculator. Okay, and it's the only time I won't feel guilty about using my calculator. I think so many of the other questions you can use your calculator, but it's the same amount of time and speed as doing it without and using the tables. Anyway, hopefully you found that video useful. Stay tuned for the next one coming shortly.